So today we're going to talk about a strategy for working backwards, like when you're given a derivative and you work backwards to that original function. And the strategy is going to help us tackle the chain rule. So last class we had three basic rules that we were reversing. We reversed the power rule, we reversed the e to the x rule, we reversed the ln of x rule. Now we're going to reverse chain rule. So I thought it'd be a good idea to just do a chain rule problem forward, refresh our memory going forward using the chain rule. So when we work backwards, we'll have those cobwebs dusted off. So let's look at this little recall box up here. It says use the chain rule to take the derivative. So derivative, we're going to be moving forward. We're going to take the derivative of this. So I'm going to rewrite my function over here just to give me some more space. Okay, so remember, when you're taking the derivative, you need to figure out what basic rule are you trying to follow. So here, this is our basic rule. We're trying to follow the basic e to the x rule, right? So this is what our basic rule says. It says if your function is written as e to the x, but instead of an x, I'm going to make that another function here. So let's make that a function because it's not a plain variable, right? When I look over here at my exponent, it's not a plain x. So that's how, remember, that's the clue. If your exponent is not a plain x, that's your clue. You need chain rule. Exponent. Oh. Hey, y'all, can you hear me? Can y'all hear me yet? Yay. Okay, sorry. That was totally my bad. I have to keep my tablet charged all the time and I had it plugged in, but the cable is really loose, so I have to be careful like not to move. um Yay, technology. Okay. Well, hopefully you had some time to try this one on your own, right? But if not, let's just pop back in where we left off there. Okay, so I was just saying that write in exponent is not a plain variable. In this case, an x, but just a plain variable, right? So it doesn't exactly follow our generic e to the x rule. So we have to use that chain rule where we just say the exponent is some function. It happens to be a quadratic function in this case, right? Our exponent's a quadratic function. So when we take the derivative, the rule says the derivative is e to the exponent, but then you tack on the derivative of the exponent. So you have to tack on that derivative of exponent. Okay, so let's go ahead and do that. So when I take my derivative, it's going to be e to this exponent, which is a quadratic function, times the derivative of that quadratic function. Okay, so that's going to be e to the exponent times, and the derivative of this quadratic function, just doing power rule, is just 2x. X is a plain variable. My base is just an x. The derivative, remember, having the derivative of x is just a 1, all that good stuff. Okay, so my derivative function will look like this, 2x e to the x squared minus 1. So show me a status. How are you feeling about chain rule? Does that dust some cobwebs off for you? Yeah? If you're taking the test to retest, this is a good review for you. Okay, so now let's reverse all that. Ready? Got to work backwards. In math, we always need a way to work backwards, right? We always have to be able to undo stuff we did, so let's do it. We're going to use a process called U substitution to work backwards. Okay, so if you notice here, my integrand is this derivative. It's just written in a different order because order doesn't matter when we multiply. We're multiplying the 2x times the e to the exponent. So that's my integrand in there. And we're going to use something called u substitution to work backwards. Okay, so here we go. Let's do it. What in the world does this look like? So I know what the answer is supposed to be. So let me just write the answer. We know the answer is supposed to be e to the x squared minus 1, because that was my original function up there, right? Yeah, e to the x squared minus 1. And technically there'll be a plus c because working backwards, there's always that possibility of a constant there. Okay, so how in the world are we going to do that? Here we go. So I'm going to rewrite my integral here just to give myself some space. And I'm going to highlight my bookends just to remind myself that this integral symbol and this dx, it's just notation. I can only use the variable x. That dx is telling me I can only use the variable x there. I only have x variables, so we're good to go. But here's the deal. We can only use one of our 3 basic reverse rules. So your first job is to figure out what reverse rule, what basic reverse rule are we using? So this is our rule. We want to use the reverse e to the x rule. So let me write it out. So the reverse e to the x rule said if you have e to the x dx, then when you reverse it, you get e to the x plus c. That's our generic rule. Okay, now here's the problem. In my generic rule, I can only use this generic rule if my exponent is a plain variable. So I need the exponent to be a plain variable. And right now I have e as my base, but my exponent is not a plain variable. So I cannot use my reverse e to the x rule right now because it doesn't fit the template. But we're going to make it fit the template using this process called u substitution. So I'm going to write out in words, we need to make the integrand, that's this thing right here, right? The integrand fit the rule. Using u substitution. Okay, so this is how u substitution works. The exponent is what's not matching the rule, right? So what we're going to do is we're going to say, okay, that exponent that's not matching the rule, I'm going to replace it with the letter u. I'm going to let u equal my exponent. Okay, I'm going to let u equal the exponent. And don't write down what I'm about to write, but just to show you, if I stopped right now, it would look like this. The integral of e to the u 2x dx. So that's matching my rule. I have a plain exponent. That's awesome. But here's the problem. Remember your bookend? So here's my bookends. My bookend has an x variable, so I need x's only. So we need x's only. And with this u substitution, I got a u variable, now I have an x variable. We can't follow my rule with different variables going on. So we can't just replace that exponent with a u. We got to go a step further. So this is what we're going to do. Let me erase that. Actually, let me just move that to the side so we can have it for later. Okay, so we're not ready yet. We can't start working backwards yet. So this is what we're going to do. We are going to get a dx in there somehow. So we're going to take the derivative of this, but instead of saying u prime for the derivative, we're going to use that fraction notation. Okay, We're going to say the derivative of u with respect to x, du over dx. Okay, so I took the derivative of the left-hand side. The derivative of u is technically u prime, but we're going to write it as du over dx. And then you just take the derivative of the other side. The derivative of x squared minus 1 is 2x. Okay, and if you notice, you probably are starting to see that I have a 2x dx. That's the problem, right? The things that aren't matching, you know, my u that I'm creating here. So I need to get this dx to the other side to be with this 2. And there's, you know, you might just see how to do it algebraically, but technically if du is being divided by dx, don't I just multiply both sides by dx? So then when I do that, boom, boom, what I'm going to get left with is a du equals 2x dx. So what that's going to allow me to do is if I see a 2x dx, I can replace it with a u. So we can replace 2x dx with a du because they're equivalent. And that's going to solve all my problems, right? Because now over here, that 2x dx is going to be a du. And look what we got now. Now I'm going to have e to the u du. So my integrand, my bookends has a u in it. My integrand has a u in it. The variables are matching. It fits my basic rule. The exponent is a plain variable. So let me write all this out, the things I'm looking for. The exponent is a plain variable. My variables match. What else am I looking for? Oh, it fits the basic rule. So this is going to fit the basic e to the x, reverse e to the x rule. The basic reverse e to the x rule. Okay, so we can just follow the rule now. So let's go ahead and follow the rule. My rule says, if I'm taking that integral, what's it going to equal? It's going to equal e to the exponent plus c. And a lot of times students will stop here, they're like, yes, I did it. But what do you think that last step is going to be? There's one more step I need to do. Any ideas? And remember, you can kind of cheat. You know what the answer is supposed to be up here. Look at what we know the answer is supposed to be, and look at what we have, and what do I need to do to make that match? Yeah, unsubstitute, right? I need to replace that u with what we originally said it was. See how I said u was this quadratic binomial there? So let's go ahead and just replace that, and boom, we're done. So I can't stop there. I need to unsubstitute. So let me make a little note here. I need to unsubstitute. Let me shrink this down. Give me 1 second. Give myself some room here. Okay, so we need to unsubstitute. Okay, so when I do all that, I'm going to get e to the x squared minus 1 plus c. And wasn't that our original function that we know because we cheated and we did it forward? You won't always have that. But you could always just take the derivative, right, and see if it actually matches. Okay, I know this is a lot. So show me a status of just how right now, and it's okay if the status is like, I have no clue what's happening. You can give me a frowny face. How are you feeling on what just happened? Are there any questions before we try another one? Yeah, no one's happy. Everyone's like, what in the world just happened? That's okay. Everything is scary the first time you see it. Let's do some more. But before I move on, I'll pause for a second. Are there any questions? Okay, here we go. Let's keep on keeping on here. Let's try another one. And just heads up, right now, I'm just going to plant a little seed so you don't hate me in a minute. Right now, all the building blocks we needed to perform that U substitution were given to us. In the next problem, they're also going to be given to us. But what we're working up to is having pieces missing that we have to like fill in the blanks. So, but first we're just going to get this U substitution process down. So let's do this. Let's try this next one. Okay. Your very first job is figure out what basic rule are you trying to match. So remember, you have 3 basic rules. The reverse power rule. So I'll write that one down. Here's our reverse power rule. Okay, we have our reverse power rule. It could be the e to the x rule. I mean, it can't be the e to the x rule because do you see an e anywhere in there? So it's not that one. And the other rule was the 1 over x dx. And I don't have any fractions. Oh, I don't have any fractions, so it's not that one. So I have to be trying to match the reverse power rule. That's my goal here. So let's try to match that. Let's try to get this mess of an integrand. Right, here's my integrand. It's all this stuff in here. I need to get this to match this so I can use my rule. Okay, so what should my u be? I have 2 choices for my u. My u is either going to be this trinomial or it's going to be the binomial. Well, I know it's going to be the trinomial because I'm trying to match something that has an exponent, right? Remember, in your power rule, in your exponent is a constant. So let's write down what we need here. Our exponent is going to be a constant. So constant exponent. And then your base needs to be a plain variable. Okay. So right now, let's see what we got. We have a constant exponent, so that's nice. We have a constant exponent. Okay, but this base is definitely not a plain x, right? Right here, this base is not a plain variable. Okay, so we need u substitution to make it match the rule. So use u substitution to match the rule, the reverse power rule. Okay, so here we go. So here's my u substitution. We're going to let u be the thing that's messing us up. The base is messing us up. So I'm going to let u be this trinomial. Okay, and again, if I stopped right there, this is what I would have. I would have u to the 5th 2x plus 3 dx. So it's not good enough just to substitute the u because now your variables don't match, right? Your bookend is telling you that you need to have x's only and you have x's and u's and you need the u. So I basically need to rewrite this with all u's, right? So let me write that down. we need to rewrite this to have all u's. Rewrite with u's only. Okay, so we're going to take the derivative of this, but instead of saying u prime, we're going to use that fraction notation. So that's going to be derivative of u with respect to x, du dx, equals derivative of x squared is 2x, derivative of 3x is 3, and technically the derivative of the constant 7 is 0, but we're not going to write that. Okay, and then I need to get that dx to the other side. So I'm going to multiply both sides by dx. Those will divide out. And that's going to give me, I'm going to keep my binomial in parentheses just to remind myself that that whole binomial got multiplied by dx. So why is this helpful? This is helpful because now if I have a this exact binomial and a dx, I can cash it in for this du. They're equivalent, right? So what I can do is over here in my integrand, I had my binomial, exact same binomial. I have the dx. All of that is going to cash in now for my du. So when we do that, it's going to look like this now. It's going to be the integral of u to the 5th du. That fits my basic reverse power rule exactly. So now you just follow the reverse power rule. So let's go ahead and do that. My reverse power rule says I would have u to the 5 plus 1 exponent over 5 plus 1 plus a constant. Okay, so that would give me u to the 6th over 6 plus a constant. And then don't forget that last step. We need to unsubstitute. So let's go ahead and do that. So when I unsubstitute this, what do I get? I'm thinking you could just leave it over a 6, but I'm thinking my math lab will pull that out to be 1/6 because there's an understood 1 in front of that u. So I'm going to write it that way just so you're used to seeing it. Whoa. So we are claiming that this function will give us our original integrand up here, that this function, if I took the derivative of it, it would give me back it would give me back this integrand. So it would be a good practice, especially if you're going to retest test 2, practice taking the derivative of that. Take the derivative of this guy and see, do you really get the original integrand back? And you should if you do your chain rule. Does anyone want to see me take the derivative of that just to see that it actually does match? Or do you trust me that if I take the derivative of this thing, this antiderivative we found, that it's going to give us the original? Probably better. Well, now that I think about it, it might be better, yeah, to do that on your own time. So because that's technically review, because we got a lot more to do. Okay, give me a status now. I'm just curious, and it can still be horrible. It can be frowny face, it can be shocked face. You can like put a vomiting emoji in the chat. Okay, it's all over the place. That's okay. Are there any questions about this one before we try another one? Okay, let me shrink this down here. I did not give us enough room to write, or maybe I'm just writing gigantic today. I don't know. Let me shrink this down. Okay. Okay, let's try another one. Here we go. So let's read this function. What function did they give us? Here are my bookends. Here's my integrin. I'm trying to fit one of my basic rules. So it's definitely not the e to the x rule, right? Because there's no e to the x in it. So that rule's out. So I only have two more choices. It's not going to be my reverse power rule because I don't see an exponent in there. I mean, technically there's an understood exponent of 1 for this one. But in the reverse power rule, there was a rule that your exponent can't be 1 when you're working with it, because remember can't be -1 when you're working with it, because remember when you add to that, it would turn into a 0 and you end up dividing by 0, and it, like, you can try it, but it's just not going to work because you're going to end up with something undefined. So this has to be the rule, the reverse ln of x rule. So let me write down that reverse ln of x rule. That said, if you add 1 over x dx, then the original function was the natural log of x, absolute value. You just slap those on to make sure your domain's okay, and then you add a c. Okay. So let's see what we need and what we have and try to make it work. Okay, so in my reverse ln of x rule, my generic template over here, I need my denominator to be a plain variable. So let me write that down. Denominator is a plain variable. Okay, that's what we need. But what do we got? Here my denominator is a linear binomial. Oh, denominator is a linear, I'll just say not a plain variable. Not a plain variable. So we need u substitution. Okay, the thing that's messing us up is what we're changing to our u, right? I need that denominator to be a plain variable, so I'm going to make it a u. So let's do that. So we're going to let u be the problem. The problem is that binomial. So I'm going to make u be that binomial. So let me see what that would look like if I substituted it. So if I substituted it, I'd have 5 over u dx. That's not good. All I do is substitute the u in there. Does my bookend variable, remember, look at your bookends. I'm supposed to have x's. Now I have u's. I need the u's, so I need everything to be u's. So let me write that in there. We need to rewrite everything with u's. So rewrite with u's only. Okay, well, let's go back to the u we need and then make it have a dx in it, right? So I'm going to come over here. We're going to take the derivative of u with respect to x. So the derivative of 4, a constant, is 0, but I'm not going to write it. And the derivative of 5x is just 5. Okay, so let's get that du alone. I'm going to multiply both sides by dx here. So du equals 5dx. So if I have a 5, which I do, and I have a dx, which I do, I can replace those with a du. So it's kind of like these guys. Let me rewrite this. I'm going to do some algebra here just to rewrite this. I'm going to pull that 5 down out of the numerator. And since order doesn't matter when we're multiplying here, it's a fraction times dx. I'm just going to pull that 5 out, and that'll leave me a 1 over u, an understood 1 placeholder when I pull that 5 out of the numerator. And then I can see I have all the building blocks I need. I have the 5. I have the dx. I'm going to replace that with my du. So now I can rewrite this as 1 over u du. Okay, so now it fits my rule. So let's make sure everything is on track here. So this, it fits the reverse ln of x rule. My denominator is a plain variable. Also, my exponents are matching, right? Not exponents, my variables match. My bookend. Okay, we're ready to go. We can use this reverse natural log rule. So let's do it. What does my rule tell me? My rule says if I have an integrand that's 1 over a plain variable, then the original function was natural log of that plain variable in absolute values plus c. Okay. So now I just need to unsubstitute. So now we need to unsubstitute. Unsub the u equals a binomial. So here we go. So that would be natural log of the binomial plus c. And that's it. We're claiming that this is the original function. So I could check myself. I won't do it today, but here's my original function. If I take the derivative of that, I should get this original integrand back. Right? Remember this original integrand? That's like your f prime of x. I'm just claiming I found a general function with a generic c in it. So if I took the derivative of that, I should get the original one back. Okay, so we've done 3 examples now. I'm still not expecting you to feel amazing. Remember, the real learning happens outside of class, right? We're just laying a foundation. But we're about to kick it up a notch. So I'm going to pause for a minute to see if there's any questions on this basic process when you have all the building blocks you need, when nothing's missing. So give me a status and I'll pause for questions. So far, we have 3 problems under your belt. Is it getting any better or are you still, it's okay if you're still terrified. Okay. We're about to kick it up a notch. And if at any time I'm going too fast, because I know these are big ideas, just, ask me to slow down in the chat or raise your hand or just unmute and say like, stop, because I know it's a lot to absorb. Okay, so what do we do when we don't have all these building blocks handed to us? Let's see. Okay. Now, I need to switch my brain over. I am going to show you the process that your textbook uses. So when you use the help tools on MyMathLab, it'll follow exactly what we're doing in the notes. It's not the way my brain likes it. And if you've taken calculus before, you might have seen a different way. It's not a bad way, y'all. There's 2 ways. If something's missing, there's 2 trains of thought, right? So one way to think about it, if something's missing, you can create what you need. That's what I like to do. But the other way, if something's missing, you just use what you have. And that's what your textbook does. And I think most students probably prefer just use what you have because there's a little less algebra involved. So that's what I'm going to do. We're going to use what we have because it's in front of our face and we're going to see it on the paper and we're going to use what we have. Okay? So I'm saying this out loud mainly for my brain because I'm going to default to my way. So I'm turning my brain on. Okay, ready? Let me take a sip of coffee before we do this. Here we go. We're going to use what we have. We're going to use what we have. Okay, what do we have? First of all, you got to figure out what basic rule we're trying to match. Definitely not e to the x rule. That one's out because I don't see an e to the x. Probably not power rule because there's an, I don't see an exponent, meaning there's an understood one and that's not allowed. So I'm definitely needing to reverse my ln of x rule. So let me write down my rule here. So we need to use the reverse ln of x rule. And I'm just writing these rules over and over again for teaching purposes, but it's not a bad idea to write them over and over again when you're doing your homework because they will not be given to you. So it'll get it into your long-term memory. Okay, so step 1, figure out what reverse rule you're trying to match. And then step 2, identify where's the problem? Why can't I use this rule? Well, to use this rule, remember, you need a plain variable there in the denominator. And right now, when I look at my denominator, it is not a plain variable. Okay, that's the problem. So that's your u. You're going to make it a plain variable. Okay, so we're going to let u be this denominator that's giving us the trouble. Okay, so if I stop right now, I'm going to have this 1 over u dx. Uh-oh. It's so close, y'all. It's so close. But can I use my rule? Nope. Because my variables are not matching. So variables do not match. We need to rewrite with only u's. Okay, so let's just continue with our steps like we normally would do. So let's take the derivative. Let's find my u prime, but remember, use that du over dx notation. Okay, so the derivative of 4x is 4. The derivative of the constant 7 is 0. We don't write it. Let's move that dx to the other side. So du equals 4dx. Okay. Now here's the problem. To get the du that I want, I need a 4, which I don't have, and a dx, which I do have. So we're missing a piece, and we're going to be the mindset we use what we have. So when I look up here, I have the dx. I don't have the 4, so we're just going to isolate the part that we have. So we have a dx, we don't have a 4. So what we're going to do is we're going to come over here and we're going to isolate what we have. So isolate what is present in the integrin. Which is only the dx. I need to get it alone, right? That's what isolate means, so get it alone. So I need to get this dx alone. It's being multiplied by 4, so I'm just going to divide both sides by 4. And then remember, there's an understood 1 exponent in front of that du, so what I really have is 1/4 du equals dx. Okay. So what is going on here? So this dx is equivalent to a 1/4 du. So we can replace dx with a 1/4 du. Okay, let's do that. We can do that. We can replace stuff. So let's come over here. Let's come to my integrin. So I'm going to rewrite the 1 over u dx right now. And then what I'm going to do is I'm going to highlight this dx and say this dx is going to get replaced with my 1/4 du because they're equivalent. So that's going to look like this now. I'm going to have a u over 1, and then I'm going to have a 1/4 du. So let's see if everything is matched. So can I use my basic reverse rule yet? I don't know. Let's see. So to use this basic reverse ln of x rule up here, I need a 1 over a plain variable, which I do, right? My u is a plain variable. So let's make sure everything's working. I have a plain variable. My variables match. They're all u's. And all, technically it matches my template, but there is this little, there is this this constant that technically doesn't match, but can't we just pull that out to the front? So I'm going to say we can pull out a constant to fit the template. Exactly. So when I do all that, this is what it's going to look like. 1/4 integral of 1 over u du. Now we fit the template exactly. Or I should say the basic rule instead of the template. Okay, so now we can follow our rule. Awesome. So I'm just going to come up here to this rule and say, okay, what's going on over here? Well, if my integrand is 1 over a plain variable, which it is, and the variables match, which they do, then my original function was natural log of the denominator. I just slap absolute values around that, and then I add a c to it. Oh, wait, what did I forget, guys? Oh my God, this is why I personally never pull out that constant. Oh my gosh. Because look, when you pull it out, isn't it super easy to forget it? Maybe it's a good thing I forgot it so y'all would see me mess up and then you'd be like, don't forget that. So I need it, that's along for the ride, and then I tack on. Okay, so this, don't forget that. I'd lose my head these days if it wasn't attached. I'm just forgetting everything left and right. Okay, and then what's your very last step before we're done? Yeah, just got to unsubstitute, right? So the very last thing I need to do is unsubstitute. So let's, from here to here, let's unsubstitute. Unsub the u equals 4x plus 7. So here we go. My answer is going to be 1/4 natural log of 4x plus 7 plus c. Okay. And remember, you can always check your work. Isn't it great that on this homework we can check our work? I'm claiming that this is my original function. Right? This thing right here. That's my original function. So if I really wanted to, I could come all the way back there. I could take the derivative of it and say, when I take the derivative, do I really get this thing over here? Because this thing is my integrand. My integrand is the derivative that I just reversed. So you could check it if you wanted to. We won't check it for sake of time. Okay, so the idea on this one was use substitution by itself left us with some stuff missing. We didn't have all the building blocks we needed to swap out x's for u's. So we had to use what we had to create an equivalent function with only u's involved. I think I heard a chime. Hold on real quick. Let me pop over here. Did I? No. Okay. Are there any questions right now about what in the world just happened? No. Normally, when we're face to face, I would give you one of these to try on your own, and I would walk around and help you pinpoint exactly where you're going wrong or give you a thumbs up if you're going right. Unfortunately, I can't do that. I can't do that in this class for time constraints, and just it's hard for me. I can't see your paper. So that's what office hours are for. That's what emailing me is for. If you're working a problem, I know these are long and have lots of steps, right? So if you're working a problem on your homework and you are stuck, take a picture, email it to me, and be like, circle where I went wrong. Like, what's right here? What's wrong? Where I know some of y'all can't come to office hours. It's inconvenient. You have to work or what have you. Just take a picture of your work, send it to me, and on my app, I'll circle it and say, this part's right. Here's where it went wrong. Here's a hint. You got to talk these things out. There's lots of steps, so there's lots of chances to mess up. Also, I posted an announcement with Madhavi Pratapa, our instructional associates, updated tutoring hours. There's also BrainFuse. You have 5 free hours of BrainFuse through Blackboard under the tools menu. And there's also our learning lab. And this stuff is just pure calculus. This is not what we're doing right here. It's not business related. You know, the word problems the learning lab might struggle with just from the business concepts, but this is just straight up pure calculus happening here. So there's lots of chances to get help. Okay. I'm going to save this real quick because this is a lot of work in case I do something silly and forget. Okay, so let's keep on keeping on. My goal was to finish the next problem, and it looks like we're right on track. We might even get a little ahead. And you know what I'll do? Let me put this on my to-do list. Since we're definitely not going to finish these notes, I will go through the My Math Lab homework and pick out which ones you should be able to do after today's lesson, so you can be working on it over the weekend, because there'll be problems that you won't be ready for, but they're at the end. But let me put that on my to-do list. Identify My Math Lab homework questions we can work now. Okay. Here we go. Let's do another one, y'all. I'm just going to give you a minute to look at that. You know what? In fact, I'm going to be quiet for 2 minutes, and I want you to try to get started. And you might completely mess up, but then at least you'll have a question for me, right? So I'm going to mute myself for 2 minutes. Just see what you would do on this, okay? Go. Hanging too long. Let's see how you did, at least if you got started correctly. So hopefully you recognize what basic rule we're trying to follow, right? So here's our basic rule. We need to do the reverse e to the x rule. So I'm going to write it out. This is the one we love, right? Oh, I love this rule. Okay. So to use this rule, what are my requirements? I need an e, which I have, right? So can't use this rule if you don't have an e. We have an e. I need my exponent to be a plain variable. And right now, that's not happening, right? Because right now, when I come over here, this exponent is not a plain variable. So we need to use our u substitution. So hopefully you recognize that your u needs to be this variable. I'm sorry. The u needs to be this exponent. Okay, and if I stopped right now, this is what it would look like. T e to the u dt. My variables are t's and u's. I need that u, so I need to rewrite it with all u's. Okay, so let's find our derivative of the u. It's du over dt. Oh, negative, so power rule on this, negative 2t. Okay, so let's get that du alone. So I need to multiply by dt on both sides. My variable's a t now. 2t. Okay, what do I got? I got to work with what I have here. So to get a du, I need three things. I need a -2. Do I have a -2 over here? Nope. Got to work with what I have. Okay, I need a t. Do I have a t over here? Yep, that's good. I need a dt. Do I have a dt in my integrin? Or in my integral? Yep, I do right there. So let's rearrange this real quick. All I'm going to do is since order doesn't matter when I'm multiplying, I'm going to move the EU first, and I'm going to move the t. I'm going to relocate it to the end of the integral, so it's right there. Okay, so I have my t dt. I need to get rid of that -2 over here. So I need to isolate what we have. What we have in the integrand, in the integral. I hear a chime. Ooh, Fidencio got an answer. I haven't done it yet. Let's see. Yo, Jane. Oh, sorry. I just saw Jane said, now I understand why your exam is split over 2 days. Yes. Okay, here we go. So to isolate that, I need to get rid of this -2. So I'm going to move it to the other side. It's gone now. So what do I have? I have, and there's an understood 1 in front of that du. So I have a -1/2 du t dt. Okay, so if I have a t, which I do, and I have a dt, which I do, that stuff I can replace with a -1/2 du. So all of this is going to get replaced with a -1/2 du. And then I'll have my du in there, which is great. So let's see what that looks like. Technically, those are multiplying, so I'll put a little... So I'm going to pause real quick because I just want to see a status. Did anyone get this far correctly? Give me a status. And if you didn't, that's okay because we're still learning. But did anyone get this far? Yay, Cassandra, high five. Fidencio, okay. And if not, that's totally okay. I'm just curious. We're just learning. If you did not get this far, I'm going to pause for a minute to see if you have any questions. Because remember, if your gut was telling you to do something different, we need to convince your gut like why that was wrong before it can absorb the right way to do it. So let me pause. Are there any questions on what I've done so far? Go ahead.
So whenever the part that I stopped at was right before we were gonna isolate everything together, like the TDT. That's the part that I didn't get. Like,
yeah, so if this method is really hard for y'all, since we won't have time to start the next, let me check real quick. Yeah, we might. I don't know if we'll have time to do the next one. I can show the other method if anyone else is curious to see it. Because it is like there's algebra in both of them. I don't know. I'm just curious, is anyone so lost right now that you would be interested in seeing the other way to do the U substitution? Everything's the same until that isolation step. Is anyone interested in seeing the create what you need instead of the use what you have? Kind of. Okay. I'll show you that step, and we're going to see, let's finish this problem. I'm going to go over this isolate what we have, the use what we have. I'm going to do that, and then I'll go over it again, and I'll show you the create what you need. Because everyone's brain is different, right? So some of y'all are going to rather use what you have, and some of y'all are going to rather create what you need, and we're all going to get the same answer in the end. So it doesn't hurt. I'll show it one time, but then after that, I'll just always default to what MyMathLab does. But some of y'all might like it better. I mean, I personally like it better, but that's because of the way my brain is wired. So let's talk about this isolate what we need. Okay. So not a trick way, but a way to think about this is come back to your integrand. So let me rewrite my integrand over here. Give me a second. I'm going to move this down. Okay, so my original problem looked like this. T e to the negative t squared dt. And all the variables are matching and we feel so good. This is what we started with, right? Everything looks great. But then it's like, oh, that does not fit my rule. So this, oops, thought that was highlighted. This part that's not fitting my rule, I had to change that to a u, right? So we changed this exponent to a u. To do that, I need to get a du in here. But I can't just randomly swap out a dt for a du. It just doesn't work that way. So I had to use what I had. So what did I have? I had the dt. Oops. I had that dt there. And then what else did I have? I had a t floating around in there. I'm like, so somehow I need to use a t and a dt to get the du. But we can only use what we have. What do we have? We made the u this exponent. We said, okay, I'm going to swap that exponent out for the u. So since I only have this u to work with, when I took the derivative of the u, it gave me a negative 2t, which was great. But I wanted du there, right? So I got the du alone. When I got the du alone, it put that dt over there. And then I was like, oh man, I have the t. I have the dt. I have everything I need, right? But I have extra. So we need to get rid of the extra. So I'm going to put a little note here. So I'm going to say we have the t and dt that we need. The negative 2 is extra. So I just got rid of the extra. And then since the extra is being multiplied, I divided it. Okay, so this extra thing here, I just divided it off. That's what I did right here. And when I divided that off, it left me just the things that I have. So I'm going to put here, replace the t and dt that we have with the thing it's equal to. It's equal to the negative 1/2 du. So that's what I did over here on this step right here. I rearranged what we had. So I rearranged the multiplication. Okay, so I just moved it to the back and then I replaced it. Then I replaced the t dt with the negative 1/2 du. Okay, I heard a little chime. Yeah, there's a lot of algebra in here. And you might have done U substitution with different types of factoring in college algebra. Trinity, did that help at all to get to that point?
Yeah, that did help. Thank you.
Okay, cool. So let's go ahead and finish this one out, and then I can show that alternate way of solving it. Okay, so, this almost fits our rule. Let's go look at to use our rule, I need I need an e, which I have, right? I need a plain variable, which I have. My variables need to match, which they do. The only technical thing here is I should technically move this constant out front. So let's go ahead and do that. So I'm going to have a negative 1/2 e to the u du. Now it fits my rule exactly. So this fits template, or I should say rule exactly. And then this one is the I don't want to say easier one, the more accessible one, because I have to remember, Kelly, I almost forgot again. I pulled out the negative 1/2, so I need to write that negative 1/2. Do not forget that. Negative 1/2. And then over here, following my rule, if my integrand is e to the u, then the original function was e to the u. Then I tack on a plus c. And now all we have to do is unsubstitute. That's it, and then we'll be done. So all I need to do is unsub the u equals negative t squared. Plus c. Oops. And again, remember, we're claiming that this thing we just found is the original function. So if you really wanted to, you could take the derivative of it and make sure that when you take the derivative, it matches the original integrin that we got. Okay. So I'm going to show you the alternate way to do the u substitution. And if you like it, great. You can totally use it. And I can totally help you with it when when you're on your homework, doing your homework and stuff. I'm going to just rewrite this real quick so I don't erase anything that I just did. Okay, so t e to the negative t squared. Okay, so here, all the steps are the same until we get to that u substitution. So I'm going to go through them kind of fast till we get to the u substitution part. Okay. So I'm going to write my basic rule over here. Here we go. So same thing as before. You're going to say, ooh, I need a plain x. I don't have it. Wait, that's not what it was. It was negative t squared. Okay. So same thing as before. You're going to say I need a plain x. I don't have it. So that's going to be my u. I'm going to make this my u. Okay, same thing as before. You're going to find the derivative of u, but you're going to use the du over dx notation, and that's going to give us negative 2t. Oh, it's not du over dx, it's du over dt, because our variable is a t. I was defaulting to an x. But in this function, my integrin has a t in it, not an x. Okay. And then I'm going to move the t to the other side, the dt to the other side. Everything is the same so far as before. Okay. So du is going to be negative 2t dt. And this is where it gets different. Here, it's just a different mindset. So before, I had to use what I was given, right? So before, when I looked at this and I said, okay, I have t e to the negative t squared dt. And I was like, okay, I replaced my exponent with a u. And the only things left to use were the t and the dt. So I was forced to only use what I had in my integrin. Well, now what we're going to do is we're just going to create what we need. What's missing? The negative 2 is missing, so we need that. So I'm going to say we need a negative 2 in the integrand. I'll put in here, it's missing. Well, I can't just randomly multiply something by negative 2. That's not mathematically okay to do, right? I can't just insert one because I feel like it. But this is what we can do. It's a little algebra trick that we use all the time in algebra. I can multiply anything in the entire world by 1 and it does not change. 5 times 1 is 5. Negative 3 times 1 is negative 3. A fraction times 1 stays a fraction. Like multiplying by 1, it's called the multiplicative identity. But multiplying by 1 doesn't change the value. And also, if you think back to fractions, remember how like the fraction 1/2 is equivalent to the fraction 3/6? 3 out of 6 is 1/2, 1 out of 2 is 1/2. We had that rule that you could multiply the numerator by anything you want as long as you multiply the denominator by the same number. And that's because what's 3 over 3? It's just 1. 3 divided by 3 is 1. That's technically, when you're getting equivalent fractions, you're just multiplying by 1, right? So this trick of multiplying by 1 is something we use a lot. Because multiplying by 1 changes the way, it can change the way something looks, but it's still equivalent to the original, okay? So equals means they look exactly the same. Equivalent means they look different, but it's the same thing. Like if I give you a dollar bill and you give me a dollar bill back, that's equal. If I give you a dollar bill and you give me 4 quarters back, it's equivalent. I mean, it's worth the same thing. It just looks different. So that's the idea. We're going to do something that looks different, but it's actually the same. Worth the same, right? Okay, so that's what we're going to do here. But instead of just multiplying by a 1, which would not be very helpful, because then everything would look the same, I'm going to do a special form of 1. I'm going to insert a -2 over -2. So I'm going to insert that. All right, insert. I'm going to insert, so instead of multiplying just by -1, I'm going to insert a -2 over -2. And you're like, how in the world does that help me? Okay, well, let's do it. Let's insert that and see what happens. So my integral is going to look like this now. I'm going to put the -2 over -2 in the front. Order doesn't matter, right? So I'm just going to put it, I'm going to insert it in there. And then I'm going to say, do I have all the things that I need for my du? Remember, to get a du, what did I need? So I'm coming back up here to this u substitution step. To get a du, I needed a -2. Do I have a -2? Yep. Okay. What else did I need? I needed a t. Do I have a t? Yep. Okay, I needed a dt. Do I have a dt? Yep. So all 3 things I needed to swap directly for a du are there. So let's think about what's happening here. So this exponent was my u, and now this -2, this t, and this dt, maybe I should loop them like this. This -2, this t, and this dt, that's all going to become my du. And I still have, it's like, I still have this thing here, but can't we just pull out a constant? Yeah, we can. Just make sure, since you're pulling it out and it's in the denominator, just keep it in the denominator. Just keep that in the denominator. Okay, so what in the world would this look like? I'm going to rearrange the algebra here just to see. I would pull out that -1/2. And then I'm going to move this e to the front, and I'm going to move the -2, the t, and the dt to the back. I'm just rearranging it to make it look prettier for my u substitution. So now my exponent is going to become my u, because then remember u is just the exponent up there. So my exponent is going to become my u. So this is my u now. So I'll have -1/2 e to the u. And then the -2, the t, and the dt, that's what I needed to get a du. To get a du, I needed a -2, I needed a t, and I needed a dt. So all of this is going to be my du. So all of that is just going to swap out for my du, and see how it fits my rule exactly now? And so when I do this u substitute, and when I do this integral and I unsubstitute, I should get the same answer that we did before. What did we get before? -1/2 e to the, okay, yeah, we should get that. I don't know. Let's see. Okay, so now I can follow my rule. Let's make sure I have all the building blocks I need to follow my rule. To follow my rule, I need a plain variable, which I have. Oh, well, first of all, I need an e to follow the e to the x rule, which I have. I have a plain variable. My variables are matching. The constant's already pulled out. We're ready to follow our rule here. So I would get -1/2, and then when I follow my rule, if my derivative is e to the u, then the original function was e to the u. I just have to tack on a c. Okay, and then I just have to unsubstitute, and then I'm done. Unsub, the u was, what was u? A -t squared. Okay, so here we go. And boom, we got the same thing as before. So we created the thing that we needed to have all the building blocks to swap out that du straight up. Instead of being limited to like what was there for us, we just use this special form of one rule. We were kind of tricky tricksters, and we forced it to have what we needed. I don't know. I like it, but it's a lot. You have to understand the special form of one, the multiplicative identity rule. You have to understand all that. It's a lot. It's a lot. I don't know. Does anyone? So Tasha says this was much better. Did anyone else like this better? Oh, you might be the only one, Tasha. Aaron said not at all. Venancio said no. That's what. See how everyone's brain is so different. Cassandra already did that for number 4. Yeah, so Tasha and Cassandra and I will just know if we were in class, we could just look each other in the eye and know we're of a different mindset, and that's okay. Everyone else, don't worry. In class, I'll do the way my math lab does it. I'll use what we have and force our hand, right? We won't get creative. This method is more creative. This method is like, I can do what I want. I can insert a -2 over -2 if I want, so this method's a little more sassy. Okay, we are at our limit for today. So obviously, oh, Marcus, yeah. There you go. Yeah, whatever, just you figure this weekend, figure out how your brain works. I'll send out an email of what problems you should be able to do so far. I'll make a video for number 6 separately, because number 6, all you would have to do on number 6 is, actually, I want to do number 6 with y'all next class. No, I'm not going to make a video for that. It's too important. So I'll send out a video of what you should be able to do. And then next class, we'll finish the last. So there's 1, 2, 3, 4 problems left. Okay. We'll finish those last 4 problems together. And I'll revamp the calendar. Let me do that. So I'm going to revamp the calendar. Okay. So y'all are good to go. You survived. Deep breaths. Work hard this weekend. Got to hit the ground running on Tuesday. Everything is scary the first time you see it. Deep breaths. Let me write on here that this was number 5 alternate method. And I'll post this answer key, even though we're not finished with it. Number 5 alternate U-sub method. Okay. Deep breaths, guys. Y'all are good to go. I'd say have a great weekend, but it's going to be a lot of math. Maybe it's a good thing I'm online and I can't see the fear on your faces right now, but reach out. I'm here to help.